Remember that data is some representation of information. And as such, one common question we have is, can I somehow compress my data? Can I somehow make my data size smaller while still maintaining the same or at least similar information? And there's generally two classes of data compression. There's what's called lossless data compression, where I can actually reconstruct my original data file exactly as is. I do not lose any of my data. There's also what's called lossy data compression, where with lossy data compression, I'm getting a compressed file that's similar to my original file, but hopefully much smaller, but at the cost of some actual data. So I can no longer reconstruct my original file, but hopefully this compressed file, this lossy compressed file, is similar enough. So for example, you might be familiar with audio compression, such as MP3. With MP3, the lower bit rate you compress your audio into, the smaller the file size, but also the lower the quality of that audio. So lossy compression, you're basically trading quality or how accurate it is to the original for the sake of smaller file size. We'll be only talking about lossless data compression. So data compression techniques where I can actually reconstruct the original file exactly as is. So let's think about this in the case of compressing strings. And specifically, I'll be talking about DNA strings. So remember, DNA strings are over the alphabet A, C, G, T. So the naive way that I represent these strings on a computer is via ASCII. I can have a text file that just contains the letter A, the letter C, the letter G, the letter T. In ASCII, A corresponds to the integer 65, C corresponds to 67, G corresponds to 71, and T corresponds to 84. And these are the binary representations of those four numbers. So remember the binary representations, each one of these is 8 bits or 1 byte. Therefore, if I wanted to represent the string ACGT in this encoding, I would have 1 byte that is this byte, the next byte would be this byte, the next byte would be this byte, the next byte would be this byte. Overall, I would take 4 bytes to represent this string. Hopefully you realize that this is kind of a waste, and using our prior knowledge of entropy, we can actually measure how much information is contained within this. Specifically, we can see that log base 2 of our alphabet, log base 2 of 4 equals 2. So given my alphabet size of 4, I should be able to represent this alphabet using only 2 bits. And this brings up the next encoding I'll talk about, called 2-bit. So instead of representing each character as a raw ASCII character, which each takes up 1 byte, I can represent it as basically a collection of 2-bit values. So the string ACGT would be encoded as 00011011, which is 1 byte. So this is a lossless compression. If you gave me the string ACGT as a 4-byte file containing the 4 bytes A, C, G, and T, I could compress this like this, such that it only takes up 1 byte instead. It turns out that for this specific string, 1 byte is the best that I can do. But in theory, if I had some arbitrary DNA sequence, so for example, if I had the sequence AAAA, could I potentially do better than 1 byte?